this case, obviously. Okay, the other experiment we've made was to see how reliable the transmission was, the communication was. So what we've done is we had 10 nodes, but we divided into groups, 5 at each end. And we varied the distance between the two groups from 1 to 20 meters, and in each of these distances we performed 150,000 tournaments. And what we've done is we've made a table of, I don't remember how many, but it was like a few hundred, not a lot because the memory of those nodes is not a lot, but we made a table of a few hundred random priorities for each node, and we computed which was the winning priority in each tournament. Okay, so we did this in sequence. When we went to the end, we started all over again in that table, so we knew, each node knew who was supposed to be the winning priority in each tournament, and we did this 150,000 times, and this is the results. And you see that even with 20 meters, the error rate is rather low. After this, it will start to increase substantially. It is almost like a step from here. It starts to degrade very rapidly afterwards.
Why is it sort of flattening out between, what is it, 17 and
yeah,
18 and 20?
I don't know. It is, but after this it will start to just increase. I don't know. Here we are probably reaching like one of those areas that sometimes it works, sometimes it doesn't, and I guess even for this amount of tournaments we might not have seen all the possibilities. So now going to the second part of the presentation, we are almost in an hour of it. I said it would be long and boring, so we will. So why don't we, having these priorities implemented in a wireless, can eventually be useful if we want to meet timing requirements. Okay, it's not all. We need to have more things sometimes, but it is useful to when we have these strict priorities implemented if we want to meet timing requirements. But as I will show you, we can use WIDOM for slightly different purposes than you might expect. And these are the examples of what we can do. We can compute, not estimate, mean and max, and estimate the number of live nodes. Sorry for that. We can do the linear election and perform interpolation of sensor data. So here is not estimating, it's computing mean and max, knowing the exact value. Estimating is the number of live nodes. So I'll show you how we can compute the minimum number, compute or collect, or I don't know exactly what to use here, but let's stick with compute. So let's say that we have these 4 nodes, and we have like this node that for some reason wants to know what is the minimum temperature among my neighbors. Okay, so how could we do that? Let's say in a normal network. In a normal network, you would just broadcast a request, say, tell me your sensor value. Nodes will eventually be able to access the medium. They will report back. We can assume that he knows how many neighbors he has. So when all of them have reported back, he can just compute the minimum, right? Easy enough. But the problem with this is that this depends on the number of nodes that he has around him, how many neighbors he has, right? So if he had 1,000 neighbors, he would have to wait for that 1,000 neighbors to all of them send him his sensor readings, and then it can compute the minimum. You can obviously figure out some slightly smarter ways to do it, but they will always depend on the number of neighbors. Okay? So what we can do is to try to use while to do this faster. How can we do that? We can do it just like this. Node A will still broadcast the request. Hey, look, give me your minimum, give me your sensor value. Or actually, you wouldn't say exactly that. You will say, look, let's start the computation of the minimum value. And what nodes do is that they start a tournament all at the same time. Okay? And they use as priority their sensor value. Okay? And if they do that, the node that wins the tournament will be the node with the minimum sensor value. And so, just by doing a tournament with while we know the minimum sensor value. Okay? And this just took the time that it takes to do a tournament. And it doesn't depend on how many neighbors he has around it. It takes the same time if he has 2 neighbors, or it takes the same time if he has 1,000 neighbors. Okay.
Under the assumption of a single domain.
Under the assumption of a single casting. Okay, so if we can imagine that we have single broadcast domains with lots of nodes, this will really have a big impact, right? Because we can do this always in the same amount of time, and we don't depend on how many nodes we have in this wireless broadcast domain. And that's kind of cool. So what I've done was, okay, let's see if we had real technology, how much time would it take, okay? Under the assumption, which is not, you might debate it, under the assumption that we are using that naive way of getting the data from all the nodes and then computing the minimum, and that's how I'm assuming that nodes are doing that with other technologies, or using while. So using while with the prototype implementation that we had, it took about 50 milliseconds to do one single tournament, okay? To do one single tournament with the new implementation takes about 10, and if we use the out of band synchronization, I don't remember, we take almost half, about 8 or 7. I'm sorry, I don't remember the exact.
I think it's much faster. I think it's 2.5 or milliseconds for the one without dependency.
It probably is.
Can
I'm just... Okay, anyway, it depends obviously on the number of priority bits, but with, I think 10, that's the usual number that we use as number of priority bits. It can be, here you can see that it's at least half, so it should be at least 5. It's probably 2, I don't remember. You remember? I don't. I'm sorry, I don't remember the exact value. So, but the comparison I'm making here is, okay, we need some technology to implement this. If we were to do it somewhere, this is our technology. This would be using, this is what I chose, using a 15.4 GTS, okay? This is just saying the minimum time that it would take to send that number of messages, the same number of messages as the number of nodes, using this technology. And by the way, if you think this is not very fair, because I'm also going to a particular standard, what I've done is do an idealized CSMA. So basically, I'm doing time division, but what I'm using as timing parameters is what a 15.4 compliant transceiver can do. So I'm just using the technology just to instantiate the bit transmission times and the minimum gap that you can have between packets. That's all I'm doing, and this is like basically a TDMA, just using the values of a 15.4 compliant transceiver. So this is not using any particular protocol, this is just using the values. And even then, you see that after 7 nodes, we are more competitive. And even our previous implementation, after 30, 35, it is more competitive than using this idealized CSMA. So this is